is an introduction to my final year project, Hybrid Deep Neural Network and Deep Reinforcement Learning for Algorithmic Finance. First, I'll be going through the research background and motivations. Next, I'll be explaining the designs as well as a summary of experimental results. And lastly, I'll be concluding with potential future works. Traditional prediction models face difficulty achieving high levels of accuracy when solving complex problems. Additionally, they lack interpretability, which is important for many legal, medical compliance, and financial systems. Using deep learning as a method to solve complex problems often comes with error-prone and arduous development. We want an architecture that is easily extendable to other complex problems with ability to adapt to environments. With this in mind, this project has two main objectives. Firstly, to implement a fuzzy deep neural network architecture and apply it to predict the stock market's movements accurately. And second, to implement a deep reinforcement learning algorithm and apply it to the portfolio allocation problem. This is the data preparation pipeline for the hybrid deep neural network. Daily stock price data is retrieved from Yahoo Finance and cleaned to remove any missing values. Stock prices are then normalized using a 14-day window. We then perform feature selection using the Monte Carlo evaluative selection method to reduce our feature dimensions. The stock price data is now ready. This diagram illustrates my proposed architecture for the hybrid deep neural network. Let's look at each layer individually. The first layer is the input layer. Each node here is the corresponding input from the processed dataset. The second layer is the antecedent layer. Each node here is defined by a membership function of the fuzzy rules. The CRIPS input values are computed against the membership function to obtain the membership values. Hierarchical clustering was used to generate the memberships. After obtaining our clusters, we perform membership adjustments to merge memberships with means that are close to each other. And the final memberships have distinct and non-overlapping means. Layer 3 comprises two paths, the deep learning path and the fuzzy path. The deep path is an LSTM network that performs the prediction task. It implicates the fuzzy membership values of the consequent segments. The fuzzy path is a set of if-then fuzzy rules induced from the antecedent and consequent layers. Each rule node encodes a fuzzy rule. Layer 4 is the consequent layer. Each node here is a label described by the membership function. This layer identifies the centers and widths from the corresponding membership functions for defuzzification at layer 5. Finally, layer 5 is the output layer, where defuzzification is performed to derive a CRIPS value for the final output. This architecture was applied to predict the T+1 daily adjusted closing price of the BVSP index. For comparison, a baseline experiment using a basic stack LSTM was done. The network could not learn to predict well, and the R-square obtained was extremely poor. Using the same dataset, we tested out the proposed architecture and obtained much better results, with a R-square score above 0.98. The architecture is then extended to predict 13 days worth of look-ahead values and managed to maintain high prediction accuracy. For the second objective of this project, we propose a deep reinforcement learning algorithm. The DRL agent uses an advantage actor-critic algorithm as it works better with large batch sizes, important for our experiments due to the large amount of data. It is also stable and more cost-effective. This algorithm uses two networks, an actor network and a critic network, which work together to maximize our reward function. Next, let's go through the variables for the portfolio environment. The state space is the observations that the agent will receive from the environment and will be the input for the agent to determine the action. We evaluate the use of historical MACD as a trend indicator, forecasted MACD, which helps to reduce the time lag of our indicator. This is obtained by using the predicted prices from the hybrid deep architecture proposed earlier. We also use a covariance matrix to incorporate risk evaluation. The action space is the actions the agent is allowed to take when interacting with the environment. This is defined as the portfolio weight of each stock and falls within 0 and 1. A softmax function is used to normalize the actions to ensure we always obtain a sum of 1. We also set a minimum base holding of 10% for each stock to help maintain portfolio diversification. The reward is the incentive for the agent to learn better actions during trading. This is the net portfolio asset value, calculated by adding returns for the day to the previous day value, less total transaction cost of buy-sell actions. This architecture was tested on an ETF portfolio using the forecasted MACD indicator and incorporating a gold hedge as well. The black line shows the resulting portfolio performance, while the grey line shows the performance of a buy and hold portfolio with the same initial weights. The colored lines are the individual results. Overall, The resulting portfolio performed much better than the baseline, achieving higher returns. Our proposed architecture allowed for flexible testing with various portfolio constraints and integration with predicted stock prices using fuzzy neural network, helping to optimize the portfolio performance. There are many opportunities for improvements and future works for my project. For a hybrid deep network, the cost of training is extremely large. Thus, it may be helpful to explore other deep structures that are more cost-effective, such as the GRU. I would also like to integrate fuzzy inference rule extraction into my architecture to achieve greater interpretability. For the deep reinforcement learning architecture, the A to C algorithm requires a large amount of training data. Thus, it will be helpful to explore other algorithms such as DTPG or the deep Q network.